On October 19th, 2017, a telescope in Hawaii catches something moving. An object tears through our solar system at 87,000 kilometers per hour. It comes from interstellar space, from between the stars. Scientists name it Oumuamua, meaning scout in Hawaiian. The object measures 400 meters long and only 40 meters wide. Nothing in our solar system looks like this. Comets are round. Asteroids are lumpy. This thing is a cigar. As it passes the sun, Oumuamua accelerates. It speeds up when it should be slowing down. No comet tail appears. No jets of gas explain the push. Scientists observe it for 11 days before it vanishes back into the void. They capture just 32 images total. In those images, Oumuamua tumbles through space in a chaotic spin. Its brightness changes by a factor of 10 as it rotates. The mathematics say this object should have torn itself apart, yet here it traveled, intact, across 4 light years of emptiness before reaching us. We will never see it again. It now races toward the constellation Pegasus, carrying answers we failed to capture. If you find this fascinating, hit that like button and subscribe. We begin now. There is an object right now, right this moment, moving away from us at 26 kilometers per second. It came from another star. It visited our solar system, and we will never, ever get it back. That's not poetry. That's just physics. And it happened while you were living your life. This is the part that gets me. Not that it exists, not that it came from somewhere else, but that it's gone, already gone, and there's nothing we can do about it. Right now, Oumuamua sits over 6 billion kilometers away from Earth. 6 billion. If you counted 1 kilometer for every generation of ancestors in your family tree, going back to the first cells that ever divided, you'd run out of grandparents around 3 or 4 billion. Oumuamua's remaining journey has more kilometers than you have ancestors. Every parent, every organism, every piece of life that had to survive long enough to reproduce so that you could exist. The object has already traveled farther than that entire chain of existence, and it's still accelerating. The discovery happened on October 19th, 2017. The Pan-STARRS telescope at Haleakala Observatory in Hawaii caught something moving against the background stars. At first, astronomers thought it was a comet, and then maybe an asteroid. Then they looked at the trajectory and everything changed. The math said this object didn't belong to the sun. It came from somewhere else, from outside, from the space between stars. Picture trying to spot a tumbling charcoal briquette in downtown Manhattan from Los Angeles at midnight. That's the detection difficulty we're talking about. The object measured maybe 400 meters long, dark, distant, tumbling through space in a chaotic rotation every 8 hours. The only reason we saw it at all was dumb luck, and the fact that it passed relatively close to Earth on its way out. Relatively close. Still millions of kilometers away. Here's the thing that most people miss. We didn't see Oumuamua coming. We only saw it leaving. The discovery happened after the object's closest approach to the sun, and it had already whipped around our star, already begun its exit trajectory back into interstellar space. We weren't watching the front door. We caught a glimpse of something already walking out the back exit. The scientists had 11 days. 11 days to point every telescope they could access at this visitor. 11 days to gather data, take measurements, capture images before it faded beyond detection. Think of it like a bullet train passing through a station where no one expected a train to exist. You hear the sound. You turn. You see it for a moment. Then it's gone into the tunnel, and you're standing there wondering if you really saw what you think you saw. The object tumbled as it moved. Every 8 hours, it completed one chaotic rotation. Its brightness changed by a factor of 10 as different surfaces reflected sunlight back toward Earth. Something long and narrow. Something spinning. The astronomers captured 32 usable images total. 32 glimpses of an interstellar visitor. That's all we have. That's all we'll ever have. They named it Oumuamua. The word comes from Hawaiian. It means scout or messenger, the first scout from distant shores. The name fits. This was the first object we ever detected that came from another star system, and passed through our own. The first confirmed interstellar visitor. Not theoretical, not mathematical, real, observable, photographed. And by the time scientists fully realized what they were looking at, the optimal observation window had already closed. Yet the best opportunity to study this thing had passed while they were still figuring out what it was. Like arriving at a crime scene hours after the fact, the evidence remains, but the moment itself is gone. You're left reconstructing what happened from traces and fragments. The telescopes kept watching as long as they could. The object grew fainter, dimmer, more distant. The measurements became less reliable. The signal degraded into noise. By early January 2018, Oumuamua had faded beyond the capability of even our most powerful instruments. Just a few months after discovery, it vanished from our ability to observe it. But it's still out there, still moving, still tumbling through the void at 26 kilometers per second. Every second, it travels 26 kilometers farther from the sun, farther from Earth, farther from any possibility of follow-up study. The distance grows, the gap widens. There's no closing it. The universe doesn't care what we find convenient. It doesn't pause for our curiosity. Oumuamua passed through our solar system on its own schedule, following laws of physics that don't consider human timelines relevant. We happened to spot it. We happened to have the technology to recognize what it was. But happening to notice something doesn't mean you get to keep it. This wasn't like discovering a new moon around Jupiter. That moon will still be there next year, next decade, next century. You can point a telescope at it whenever you want. You can plan missions. You can gather more data as technology improves. Oumuamua allowed none of that. It appeared. It departed. The show ended before most of the audience even knew it had begun. What remains now is detective work. Those 32 images. The measurements taken during that frantic 11-day window. The spectroscopic data. The brightness variations. The trajectory calculations. Scientists have to reconstruct the nature of this object from glimpses and fragments. They have to build a complete picture from incomplete information. They have to answer questions about an object they can no longer observe. And some of those answers got strange. Very strange. But that comes later. For now, what matters is understanding the reality of the situation. We found something. We watched it. We lost it. That sequence of events happened in real time, in our solar system, during our lifetimes. This isn't ancient history. This isn't a theoretical exercise. And this is something that occurred while you were going to work, sleeping, living your ordinary life. An object from another star passed through our neighborhood and left before we could properly introduce ourselves. It's gone now, moving toward the constellation Pegasus, moving away from everything we know, and every second that passes, it gets farther. Every second that passes, it gets farther. Let's talk about what that actually means. At its closest approach to the sun, Oumuamua was moving at 87 kilometers per second. That's 87,000 meters every single second. If you could drive that fast on a highway, you'd cross the entire United States in under a minute, coast to coast, 47 seconds. And that's how fast this object was traveling when it whipped around our star and began its exit from the solar system. It's slowed down since then. Out beyond the sun's strongest gravitational pull, it's cruising at about 26 kilometers per second relative to the sun. That's still fast enough to circle the Earth in just over 25 minutes. You could start at the equator, pass over every ocean and continent, and arrive back where you started before your coffee got cold. But speed only tells you part of the story. Distance tells you the rest. Right now, as you're listening to this, Oumuamua is more than 6 billion kilometers away from Earth. If you started counting 1 kilometer per second when Oumuamua was discovered back in October of 2017, you'd still be counting now. And you wouldn't finish counting its current distance for another 76 days. 2.5 months of counting. 1 number per second, no breaks, no sleep. That's the gap between us and this object. Light from the sun takes 8 minutes to reach Earth. That's our baseline. Our morning sunlight left the sun's surface while you were brushing your teeth. The same light, traveling at the same speed, takes 5.5 hours to reach where Oumuamua is right now. 5.5 hours. That's the same amount of time it takes sunlight to reach Pluto at its average distance from the Sun. Think about that. An interstellar visitor, something that came from another star system entirely, is already as far from us as Pluto. It's already back in the outer reaches of our solar system, heading for the edge. Here's another way to understand the distance. Picture yourself getting into a car at the moment Rome fell, the year 476. The Western Roman Empire collapses, and you start driving. You never stop. You don't sleep. You don't age. You don't die. You just drive, at highway speed, for 1500 years, through the Middle Ages, through the Renaissance, through industrialization and world wars, and the space age. You'd arrive at Oumuamua's current location just in time to watch our sun begin its death throes, billions of years from now. Actually, that's not quite right. You still wouldn't be halfway to where Oumuamua will be when your grandchildren die. The numbers break human comprehension at this scale. The object has been traveling for more than 6 years since we discovered it. 6 years of constant motion through the void. By the late 2020s, it will be beyond the equivalent distance of Neptune's orbit. That's the 8th planet from the Sun, the boundary most people think of when they picture the edge of the solar system. Oumuamua will have crossed our entire planetary system in less than 2 decades. And here's the part that should make you pause. Oumuamua is already farther from us than Pluto is at its average distance from the Sun. Read that again. An object that came from another star, that traveled through interstellar space for millions or billions of years, visited our solar system for a brief moment, and is now, in practical terms, already back in interstellar space. It came through like someone cutting across your yard, and it's already at the neighbor's house 3 blocks away. The 11 days we had to observe it weren't just brief. They were a statistical miracle wrapped in a tragedy. A miracle because we spotted it at all. Pan-stars could have been pointed anywhere else that night. The object could have passed through during daylight hours. It could have come from an angle we don't monitor as carefully. We could have missed it entirely, and we would never have known. But it's also a tragedy because 11 days is nothing. Not enough time to plan a mission. Not enough time to reposition our best telescopes. Not enough time to do anything except watch and measure and hope you're recording the right data. Those 32 images had to be enough. The spectroscopic readings had to be enough. There would be no second chances. The universe doesn't care what we find convenient, yet it doesn't adjust its schedule for our readiness. Oumuamua appeared, performed its flyby, and departed on a timeline completely indifferent to human preparation. We were astronomers trying to study a train that had already left the station while we were still buying tickets. And now it's gone. Not just out of sight, gone in a way that matters. Even if we could see it, even if we had a telescope powerful enough to resolve it at this distance, we couldn't learn anything new. The object is too far, too faint, too fast. Every instrument we have is now pointed at a memory. Every calculation we make is based on observations that ended in October of 2017. This is the reality of interstellar visitors. They don't wait. They don't slow down for our benefit. They pass through our neighborhood on trajectories determined by gravitational forces that began millions of years ago. We get the time we get, and then they're gone forever. Oumuamua is heading toward the constellation Pegasus. It will never return. Not to our solar system. Not to whatever system it came from. It's on a journey that will outlast our species, our planet, possibly our sun. And we had 11 days with it. So what exactly was this thing that moved so fast and disappeared so quickly? What did those 11 days of observation actually tell us? That's where things get interesting and strange. The thing about Oumuamua is simple. It came from somewhere else, not from the outer edges of our solar system, not from the Kuiper belt where comets are born, not from the Oort cloud, yet that distant shell of ice and rock that still orbits our sun, somewhere else, another star system entirely. Oumuamua is the first confirmed interstellar object ever detected passing through our solar system, the first one we've ever seen. In the entire history of astronomy, we had never confirmed an object from interstellar space moving through our neighborhood. Not once. Think about that for a moment. Humans have been watching the sky for thousands of years. We've catalogued millions of objects. Asteroids, comets, rocks of every size and shape. We've tracked their orbits, calculated their compositions, predicted their paths decades into the future. Every single one of them was born here. Every single one belongs to our solar system, bound to the sun by gravity, as circling in orbits that began when the planets formed 4.5 billion years ago. If our solar system were a small town, Oumuamua is the first confirmed stranger we've ever seen just passing through. Everyone else we've ever met was born here. Every asteroid, every comet, every rock, they're all locals. This thing is from somewhere else. The key evidence is its trajectory. Scientists call it hyperbolic. That word matters. It tells you everything about where Oumuamua came from and where it's going. Picture throwing a ball straight up into the air. It goes up, slows down, stops, then comes back down. That's a parabolic trajectory. Gravity wins. The ball returns. A hyperbolic trajectory is different. It means the object is moving fast enough that gravity can't pull it back. It just keeps going, never returning. Oumuamua's trajectory is hyperbolic relative to the sun. It came in from interstellar space, swung around our star, and headed back out. The sun's gravity bent its path, changed its direction, but couldn't capture it, couldn't make it stay. The object is gravitationally unbound. Those are the technical words. What they mean is simple. Oumuamua doesn't belong to us. It never did. We can trace its path backward through space. The calculations show it came from the direction of the star Vega. Vega is 25 light-years away. That's 150 trillion miles. At highway speed, that drive would take about 300 million years. 300 million years of nothing but empty space and darkness. Except Vega wasn't actually there when Oumuamua passed through that region of space. Stars move, Vega moves. On 300,000 years ago, when Oumuamua was passing through the area we now associate with Vega, that star was somewhere else. We don't know where Oumuamua actually came from. We just know the direction it arrived from. The origin point is lost to time. The object itself is strange. Best estimates from how its brightness changed over time suggest it's about 400 meters long and 40 meters wide. That's roughly 4 football fields in length and about half a football field across, shaped like a cigar or maybe a pancake. The light curve data is consistent with both shapes. We don't have pictures. We never got close enough. All we have are brightness measurements, and those measurements tell us something was tumbling through space, reflecting light as it spun. The color is reddish, similar to some objects in the outer reaches of our solar system. That reddish hue suggests a surface coated in organic molecules, compounds of carbon that have been irradiated by cosmic rays over millions of years. It's the color of something old, something that's been traveling through the galaxy for a very long time. Here's what makes it stranger. There was no visible coma, no cloud of gas and dust surrounding the object. When comets from our solar system approach the sun, they heat up. Ice turns to gas. Dust gets released. You see a glowing cloud around the nucleus, sometimes a tail stretching millions of miles behind it. Oumuamua showed none of that. Despite coming close enough to the sun that a comet should have started out gassing, astronomers saw nothing. No coma, no tail, just a dark object reflecting sunlight. And that absence of a coma suggested maybe it wasn't a comet. Maybe it was an asteroid, a rock, not a snowball. But then the object did something asteroids don't do, something comets do. But Oumuamua supposedly wasn't a comet. It accelerated. As it moved away from the sun, speeding toward the outer solar system and eventually back to interstellar space, it moved slightly faster than it should have. Not by much, just a tiny deviation from the expected trajectory. But the deviation was there, measurable, real. Imagine a grain of sand thrown from Earth somehow reaching Mars and then speeding up in empty space. No engines, no thrust, nothing pushing it, just acceleration where there shouldn't be any. That's what Oumuamua did. Gravity alone couldn't explain it. The sun's gravity pulls things toward it, not away from it. As objects move farther from the sun, they should slow down slightly, compared to what pure orbital mechanics predict, or at least move exactly as predicted. They shouldn't speed up. Oumuamua sped up, not by a lot. The acceleration was small, subtle, barely detectable, but it was there. This is the central mystery, the thing that keeps scientists arguing and publishing papers and building models years after the object disappeared from view. Oumuamua experienced non-gravitational acceleration. Something pushed it. Something gave it a boost as it left our solar system. We don't know what. We have theories, lots of theories, some mundane, some exotic, some that sound like science fiction, but we don't know. The object is gone now. Too far, too faint, moving too fast to study anymore. All we have left are those 11 days of observations, brightness measurements, trajectory data, color estimates. That's it. And somewhere in those numbers is a clue to what Oumuamua actually is, what made it accelerate, what sent it on its journey through the galaxy millions of years ago. The answers are in the data. We just have to figure out how to read them. Before Oumuamua, interstellar objects were theoretical. Scientists knew they must exist. The galaxy is full of planetary systems. During the chaotic early days of planet formation, objects get ejected. Gravitational interactions fling rocks and ice into interstellar space. Those objects drift through the galaxy for millions or billions of years. Statistically, some of them must pass through our solar system occasionally. The math said so. The simulations confirmed it. Interstellar visitors should be out there. We'd just never actually seen one. Oumuamua wasn't the first to pass through. It was just the first time we were looking carefully enough to notice. Our telescopes finally got good enough. Our survey programs finally comprehensive enough. We finally had the tools to spot something small and fast and dark moving through the inner solar system. Oumuamua happened to arrive at the exact moment in human history when we could detect it. A few decades earlier, we would have missed it entirely. It would have passed through unnoticed, like all the others probably have for billions of years. That timing matters. It means there are others. There have always been others. They're passing through right now, moving through the space between planets, and we're not seeing them because they're too small, or too far off the ecliptic, or moving too fast. Oumuamua is the first, and it won't be the last. We're watching now, we're ready, and the question hanging over all of it, the question that drives every new paper and every new analysis, is simple. What could make an object speed up without any visible means of propulsion? What pushed Oumuamua as it raced back toward the stars? Something pushed Oumuamua, not by much, but enough that we noticed. When you track an object through space, you're playing a game of prediction. You measure where it is. You measure how fast it's going. You calculate the gravitational pull from the sun, from the planets, from everything massive enough to matter. Then you predict where it should be tomorrow, next week, next month. The math is precise. We've been doing this for centuries. We're very good at it. Oumuamua didn't show up where the math said it should. The deviation was small, roughly 17 meters per second. That's about 38 miles per hour. It's the speed you'd gain falling off a 5-story building. Not fast in human terms. But Oumuamua wasn't standing still when it gained that speed. It was already moving faster than a bullet, and it gained 17 meters per second sideways, in the vacuum of space, with no visible means of propulsion. Let me put that in perspective. Picture trying to change the direction of a boulder by blowing on it. Not a pebble, a boulder. Potentially millions or billions of kilograms of rock and ice, and it's already screaming past you faster than anything you've ever seen. Your breath wouldn't do anything. It wouldn't even register. But something gave Oumuamua that push. Something accelerated it in a way gravity alone couldn't explain. Yet this kind of thing has a name. Non-gravitational acceleration. It means exactly what it sounds like. A change in velocity that gravity can't account for. The object speeds up or slows down or changes direction. And when you run the numbers, the gravitational forces don't add up to explain it. There's a gap, a mismatch between prediction and observation. Scientists measure this through astrometry, precise position measurements over time. You photograph the object against the background stars. You do it again a few hours later, again the next night, again and again. Each image gives you a position. String those positions together and you get a trajectory. Compare that trajectory to what gravity predicts. If they match, you're done. If they don't, something else is pushing. Oumuamua's trajectory didn't match. Here's the thing. Non-gravitational acceleration isn't weird. Comets do it all the time. In fact, it's one of the ways we identify comets. As a comet approaches the sun, it heats up. Ice on the surface starts to sublimate. Solid ice becomes gas without passing through liquid. That gas erupts from the surface in jets. Those jets act like tiny rocket thrusters. They push the comet, not much, but enough to change its path slightly. Enough that when you calculate where the comet should be based on gravity alone, it's somewhere else. We've observed this in hundreds of comets. It's normal. It's expected. The outgassing creates a visible coma around the nucleus, a cloud of gas and dust that can stretch thousands of kilometers. As the comet gets closer to the sun, the coma grows. Eventually, it forms a tail, sometimes two tails, one of dust and one of ionized gas, both streaming away from the sun. The whole display is bright enough to see from Earth, sometimes with the naked eye. That's what comet outgassing looks like. Bright, obvious, unmistakable. Oumuamua showed the acceleration. It just didn't show the outgassing. Every telescope that looked at it saw the same thing. No coma, no tail, no jets of gas erupting from the surface, no dust cloud, nothing that would indicate active sublimation. It looked dead, inert, just a dark, tumbling rock catching sunlight as it spun. But it was accelerating exactly like a comet would. The pattern matched. Smooth, consistent, not random or chaotic. The kind of gentle, steady push you'd expect from outgassing as an object swings past the sun. Imagine tracking a car with GPS. You know its speed, yet you know its direction. You predict where it should be in 10 minutes. When 10 minutes pass, you check. The car is 50 feet away from where you predicted. Not ahead or behind on the road. 50 feet to the side. But there are no tire marks leading to that new position. No skid marks. No evidence of how it got there. The car just moved, and you can't explain how. That's what this was like. The evidence of a cause without the cause itself. The measurements were checked and rechecked. Different teams analyzed the data independently. They all came to the same conclusion. Oumuamua deviated from a purely gravitational trajectory by about 17 meters per second. The acceleration was real. It wasn't a measurement error. It wasn't an artifact of the data. Something pushed Oumuamua, and that something behaved exactly like outgassing. But there was no outgassing visible to any instrument we pointed at it. Think about finding wet footprints on a dry sidewalk. The footprints are clear, fresh. You can see where someone walked, but you look around and there's no water, no puddles, no sprinklers, no rain. The sidewalk is bone dry everywhere except those prints. The evidence tells you water was there, but the water itself is nowhere to be found. That's the ghost thruster, an acceleration with no visible source, a push with no hand doing the pushing. The physics made sense. The pattern made sense. Objects don't just accelerate in space without a reason. Forces require sources. But when scientists looked for the source, they found nothing, just empty space and a tumbling object that shouldn't have changed course. The deviation wasn't dramatic. 17 meters per second sounds small against the backdrop of interstellar space. But precision matters in astronomy. We track objects across millions of kilometers. We predict positions months in advance. A deviation of 17 meters per second compounds over time. It adds up. By the time Oumuamua left the inner solar system, that acceleration had shifted its path significantly, enough that if we'd tried to send a probe to intercept it based on the initial trajectory, we would have missed. The probe would have arrived at empty space, searching for something that was already long gone. This wasn't a subtle effect that only appeared in the margins of error. This was clear, measurable, undeniable. Oumuamua changed speed in a way gravity couldn't explain, and it did so smoothly and consistently, exactly mimicking the behavior of something outgassing. But the outgassing wasn't there. The contradiction sits at the heart of everything that followed. Every theory, Every paper, every debate. You can't have acceleration without a force. You can't have a force without a source. But Oumuamua seemed to break that rule. It accelerated like a comet, looked like an asteroid, and defied every attempt to reconcile those two facts. So, what was it? What could create that smooth, consistent push without leaving any trace? What kind of object behaves exactly like something we understand, while refusing to show us the mechanism we expect? Before we talk about what Oumuamua is, we need to address a simpler question. What did it look like? What was its actual shape? You'd think we'd know this. We tracked it for weeks. Multiple telescopes, multiple observations. But here's the thing. We never actually saw it. Not directly, not in any way that would let us say with certainty what form it took. Every image you've seen of Oumuamua is an artist's interpretation. Those famous renderings of the elongated reddish rock tumbling through space. Pure guesswork, educated guesswork, sure, based on real data, but still guesswork. What we had wasn't a photograph. It was a light curve, a record of how bright Oumuamua appeared over time as it rotated. That brightness changed. A lot. And from those changes, we had to infer everything else. The brightness varied by a factor of 10 to 1. That's dramatic. Imagine watching a distant lighthouse. Now imagine that lighthouse gets 10 times brighter, then 10 times dimmer, in a regular pattern. Something about that object's shape or orientation is changing. That's what Oumuamua did. Every 8 hours, the pattern repeated. Bright, dim, dim. An 8-hour rotation period. If you were standing on Oumuamua, sunrise to sunrise would take as long as a full workday. Not particularly fast for an object its size. But that rotation alone didn't explain the brightness changes. The 10 to 1 variation told astronomers something crucial. Oumuamua wasn't round. Round objects don't change brightness that much when they rotate. They present roughly the same surface area no matter which way they're facing. To get a 10 to 1 ratio, you need something elongated, something with a dramatically different profile depending on your viewing angle. The best fit models suggested dimensions around 400 meters by 40 meters, a 10 to 1 aspect ratio. When I said Oumuamua is 400 meters long, actually, that's not quite right. Let me try again. We think it might be 400 meters in its longest dimension if it's elongated like a cigar, but it could also be disc-shaped. We're guessing based on how its brightness changed. We never actually saw its shape. That 10 to 1 aspect ratio is more extreme than any known asteroid or comet in our solar system. Nothing we've catalogued comes close. Most asteroids are lumpy potatoes. Elongated, sure, but not like this. Not a 10 to 1 ratio. That's genuinely unusual. It suggests something about Oumuamua's formation or history, set it apart from the rocks we're used to seeing. The rotation wasn't simple either. Oumuamua wasn't just spinning around a single axis like a football spiraling through the air. It was tumbling, complex rotation, multiple axes. Picture a hubcap flying off a car and bouncing down the highway. That chaotic wobble. That's closer to what Oumuamua was doing, tumbling through interstellar space with this strange, elongated form. The light curve captured that complexity. The brightness didn't just fade in and out smoothly. It had structure. Variations within variations, signs of an object rotating in multiple dimensions at once. But here's where it gets tricky. A light curve can't tell you everything. It can tell you that an object has an elongated profile. It cannot tell you which kind of elongated profile. But think of it like determining the shape of a car at night by watching how its headlights flicker as it tumbles down a hill. You can deduce that it's elongated. You can measure how elongated. But you can't tell if it's a limousine or a motorcycle lying on its side. Both could produce similar flicker patterns. Oumuamua's 10 to 1 brightness variation could mean a long cigar shape, 400 meters long, 40 meters wide, like a cosmic pencil. That's what most of the early illustrations showed. That's probably what you picture when you hear the name. But it could also mean a flat disc, a pancake, 400 meters across, 40 meters thick, viewed edge on most of the time, face on occasionally. The light curve fits both interpretations. We can't distinguish between them from brightness alone. And this is watching a security camera recording of a crime that happened while the camera was off. We're inferring the shape from shadows and reflections, not from actually seeing it. The data is real. The measurements are solid. The interpretation is uncertain. Every paper that talks about Oumuamua's shape includes caveats, phrases like consistent with and best fit model, and assuming a uniform surface. Scientists being careful with language because they know the limits of what they observed. Some researchers favor the cigar model. It matches the behavior of certain cometary fragments, objects that have been stretched and deformed by tidal forces during close passes to stars. Others point out that a disk shape might explain some of Oumuamua's other strange properties. And a flat pancake would interact with sunlight differently than a long needle. That matters when you're trying to explain acceleration without outgassing. But we're getting ahead of ourselves. The point is this: we detected an object. We tracked its motion. We measured how its brightness changed. From that sparse data, we constructed models. Those models gave us possible shapes. Not definite shapes, possible ones. Every illustration, every rendering, every artist's conception is choosing one interpretation over another, making the invisible visible through educated guesswork. The tumbling adds another layer of mystery. Why was Oumuamua tumbling at all? Objects in stable orbits around stars tend to settle into simple rotations over time. Tidal forces even them out, but Oumuamua wasn't in orbit around anything, yet it was flying free through interstellar space. That tumble could be ancient, a remnant of whatever event sent it wandering in the first place. Or it could be recent, the result of an encounter we didn't witness. We don't know. That 8-hour rotation period is actually on the slower side for small solar system bodies. Many asteroids spin much faster, hours or even minutes. The fact that Oumuamua rotated relatively slowly might mean something, or it might mean nothing. Without knowing its internal structure, its density, its history, we're just collecting data points without context, building a profile of something we never clearly photographed. We measured it, we tracked it, we recorded every photon we could catch, but in the end, we're arguing about the identity of something we never actually saw: a brightness curve, a rotation period, a 10-to-1 ratio. That's what we have. Everything else is interpretation, models fitted to sparse observations, the best guesses of people trying to reconstruct a shape from its shadow. And those guesses matter, because the shape you assume determines how you explain everything else. The acceleration, the lack of outgassing, the strangeness that refuses to resolve into something familiar. We built theories on a foundation we can't quite see clearly, and that foundation is shakier than most people realize. There's a fundamental problem with everything we've discussed so far. We don't know how much Oumuamua actually weighs, and that matters more than you might think. Astronomers have 3 standard methods for determining the mass of a distant object. The first is gravitational influence. And watch how it tugs on nearby objects. Measure those distortions. Calculate backward to find the mass. But Oumuamua didn't pass close enough to anything we could measure. No spacecraft flyby. No gravitational fingerprint left behind. That method was impossible. The second method relies on composition. If you know what something is made of, you can estimate its density, then use the size and density to calculate mass. Simple math. But here's the problem. We don't really know what Oumuamua is made of. The third method is direct measurement. Send a probe, land on it, weigh it. We didn't do that either. So what did we have? Light. Reflected sunlight caught by telescopes. That's it. Trying to weigh someone by looking at their shadow and guessing their bone density. That's essentially what astronomers did with Oumuamua. And they used spectroscopy. Every material absorbs and reflects specific wavelengths of light. It's like a fingerprint. Iron looks different from ice. Rock looks different from metal. Capture enough photons and you can identify what you're looking at. Usually, Oumuamua appeared reddish in the limited spectra we captured. That red color is consistent with organic compounds, or tholins. Those are complex organic molecules created when simpler chemicals get bombarded by cosmic radiation. We see that reddish tint on Kuiper belt objects, on some asteroids, on surfaces that have been sitting in space for millions of years. That suggested something. Maybe Oumuamua was rich in organics. Maybe it had a carbon-based composition. Scientists used that reddish color to estimate density, somewhere between ice and rock, and then they estimated size from brightness, combined those numbers, got a mass estimate. But there's another measurement that matters: albedo. That's how much light an object reflects versus how much it absorbs. A mirror has high albedo. Coal has low albedo. The brighter something appears, the higher its albedo might be. Or it might just be bigger, or closer. You can't tell without other information. Oumuamua's albedo came in around 0.1. That means it reflects only 10% of the light hitting it. The rest gets absorbed. That's pretty dark. Similar to carbonaceous asteroids. Similar to dormant comet nuclei. Dark objects with organic-rich surfaces. Here's where it gets complicated. Brightness depends on both size and reflectivity. Imagine trying to determine if a sealed box is full of feathers or lead just by watching how its brightness changes as it spins. You can make guesses, but you're fundamentally limited. A small shiny object can look identical to a large dark one. Same brightness, different reality. The mass estimates for Oumuamua range from 40,000 tons to 400,000 tons. That's a factor of 10 uncertainty. Think about what that means. The difference between a large office building and a small mountain. Both could fit the observations equally well. 40,000 tons is roughly the mass of a large cargo ship. 400,000 tons is a decent-sized mountain. Those are not the same thing, not even close. And we can't say which is right. That 10 times uncertainty ripples through every calculation. A mass determines how much force is needed to produce acceleration. If Oumuamua is light, even a tiny force could push it off course. If it's heavy, you need something much stronger. The theories that explain its acceleration depend entirely on which mass you assume. Low mass favors outgassing. A little bit of vaporized ice could provide enough thrust. High mass makes outgassing harder to justify. You'd need more gas than seems plausible, given what we observed, or didn't observe. The reddish color that suggested organic materials on the surface. That coating might be only microns thick. Interstellar radiation bombards objects over millions of years. It creates a reddish organic crust on almost anything, regardless of what's underneath. Ice, rock, metal, doesn't matter. Give it enough time in deep space and it'll develop that reddish patina. We might be seeing the equivalent of paint on a surface and assuming the whole object is made of paint. The interior could be completely different. Pure ice beneath that organic crust, or solid rock, or metal, or something we haven't considered. That thin surface layer tells us almost nothing about bulk composition. This is the detective work of astronomy. You can't touch the evidence, can't sample it, can't examine it up close. You collect photons, you build models, you make assumptions and hope they're close to reality. Every density assumption leads to a different mass. Every mass leads to different physics. The uncertainty compounds. It spreads through the calculations like cracks through ice. Without knowing mass precisely, we can't calculate the exact force needed for that observed acceleration. We can't say whether outgassing explains it, or whether something else is required. The numbers stay fuzzy. The theories stay open. Nothing resolves. This is why scientists argued so intensely about Oumuamua, not because anyone had definitive proof, but because the uncertainties were large enough to accommodate wildly different explanations. A dark comet could work. A nitrogen iceberg could work. Even a light sail couldn't be ruled out completely. The math bent to fit multiple scenarios. And that mass uncertainty of 10 times means we're essentially guessing, building theories on quicksand. The foundation wobbles, and everything built on top wobbles with it. The brightness we measured could mean a small, bright object, or a large dark one. The reddish spectrum could mean organic-rich composition throughout, or a thin radiation-damaged surface hiding something else entirely. The low albedo could indicate carbon compounds, or just a surface that's been weathered and darkened over time. We measured what we could. We did the math. We made our best estimates. But in the end, we're trying to weigh a ghost, something that passed through quickly and left only shadows, only echoes in our data. That's the truth about Oumuamua's mass. We don't know it. Not really. We have a range, a bracket of possibilities. And that range is wide enough to drive entire competing theories through. Every scientific paper about Oumuamua's acceleration starts with an assumed mass, a number picked from that wide range. Then, the calculations flow from there. Different assumptions lead to different conclusions. The mystery doesn't resolve because the foundation remains uncertain. So when you read about theories explaining Oumuamua's behavior, remember this. They're all built on mass estimates we can't verify, on density assumptions based on surface colors that might not represent the interior, on brightness measurements that could mean multiple things. We're fitting models to incomplete data, arguing about explanations for an object we never properly characterized. That acceleration we measured is real. The change in velocity happened. But explaining it requires knowing the mass, and the mass remains somewhere between a building and a mountain, both equally plausible, neither confirmed. We're arguing about an object we couldn't weigh, building models on assumptions, trying to explain behavior we can barely measure. That acceleration is the center of everything. But to understand what caused it, we need to talk about invisible wind. Think about launching a paper airplane. It leaves your hand and glides. Maybe it rises slightly on an updraft, but imagine it gains speed after leaving your hand. No wind, no explanation, just acceleration with no visible cause. That's what outgassing can do to an object in space. It provides thrust, a push, but we need to see the wind to believe it happened. Most comets make that wind obvious. They announce themselves. When a comet approaches the sun, solar radiation heats its surface. Frozen compounds begin to sublimate. They transition directly from ice to gas without passing through liquid. Water ice turns to vapor. Carbon dioxide boils away. The gases stream off the surface, carrying dust particles with them. This creates the coma, the fuzzy envelope of material surrounding the nucleus. Sometimes it creates a tail, millions of kilometers of glowing gas and dust pointing away from the sun. These features are visible, detectable, undeniable. The compounds responsible have specific signatures. Water ice, chemical formula H2O, carbon dioxide, CO2, carbon monoxide, CO, methane, CH4, ammonia, NH3. Each one absorbs and emits light at particular wavelengths. Astronomers use spectroscopy to identify them. Yet we point our instruments at the coma and read its chemical composition like a barcode. The gases glow faintly in specific colors. They reveal themselves. Oumuamua showed none of this. No coma, no tail, no spectroscopic signature of outgassing, just empty space around a tumbling object. That's why the acceleration seemed so strange. If something was pushing it, where was the evidence? The answer might lie in understanding when different compounds sublimate. Each one has a threshold temperature. Get warm enough and the ice can't hold together anymore. It has to become gas. Water ice sublimates at around 200 degrees Kelvin. That's cold by Earth standards, about -73 Celsius. But it's relatively warm in space terms. An object needs to get fairly close to the sun before water ice starts boiling away. Around Jupiter's orbit is where it typically begins. Carbon dioxide sublimates much earlier, at around 80 degrees Kelvin. That's -193 Celsius. CO2 ice starts outgassing well beyond Jupiter, out past Saturn's orbit. The sun's heat is enough to turn it into gas. Carbon monoxide goes even further. It sublimates at just 25 degrees Kelvin, way out there, beyond Uranus, almost to Neptune. Here's the surprise. Oumuamua could have started outgassing when it was still farther from the sun than Neptune, long before anyone was looking for a coma, long before we had any idea it existed. By the time we spotted it, the process might have been nearly finished. Tank almost empty. The visible signs we were looking for might have already dissipated into space. Yet we arrived at the scene after the evidence had scattered. That assumes the outgassing produced visible signs in the first place. Most comet outgassing is like smoke from a fire. Obvious, visible, detectable from a distance. You see the plume and know something's burning. But there's another possibility. Hydrogen outgassing would be like carbon monoxide from a fire, just as real, just as present, but invisible, harder to detect. You need special instruments. You need to know to look for it. Molecular hydrogen, H2, doesn't play by the same rules. It's the simplest molecule. Two hydrogen atoms bound together. It doesn't have the complex structure that makes other molecules easy to detect spectroscopically. In optical wavelengths, it's essentially transparent. In infrared, where we usually look for cold objects and gases, it barely shows up. An object could be venting hydrogen into space, and we'd have a hard time seeing it happen. The physics works. Hydrogen can provide thrust just like water vapor or carbon dioxide, maybe more efficiently because it's so light. Each molecule carries less mass but moves faster when heated. It could explain the acceleration without producing a visible coma. Invisible wind pushing an invisible object through empty space. But there's a problem, a big one. Hydrogen ice requires extreme cold to form. We're talking about 3 to 10 degrees Kelvin. That's 3 to 10 degrees above absolute zero, the coldest temperature possible in the universe. The coldest natural temperature recorded on Earth is around -89 Celsius. That's 184 Kelvin. To freeze hydrogen, you need conditions colder than that by about 170 degrees, maybe more. These temperatures barely exist. You find them in deep space, in the darkest regions between stars, in molecular clouds where new stars haven't formed yet to heat things up, in laboratory experiments where scientists spend enormous effort to chill samples to near absolute zero, not in normal cosmic environments, not on objects we regularly observe. Here's the thing. We don't really know if objects with frozen hydrogen surfaces can even form naturally in the galaxy. That's the honest answer. The temperatures required are so extreme that some scientists argue such objects shouldn't exist. There's nowhere cold enough for hydrogen ice to accumulate in meaningful amounts. Others argue they must exist. The universe is vast. And molecular clouds get cold enough. Maybe some objects form in those conditions and get ejected before warming up. And we can't settle it because we've never sampled one. We've never visited an object and measured its surface composition directly. All our data on comets and asteroids comes from remote observation, from light analysis, from inference. We've sent probes to a handful of comets. We've landed on one, but those were all objects from our solar system, born in conditions we understand. Oumuamua came from somewhere else, formed under different circumstances, with a thermal history we can only guess at. The hydrogen hypothesis requires us to accept something we've never seen, an object so cold at formation that molecular hydrogen froze on its surface. And then, that object traveled through interstellar space for millions or billions of years. Somehow, it retained enough of that hydrogen ice to produce detectable acceleration when passing through our solar system, despite cosmic rays, despite rare encounters with dust grains, despite the slow warming that happens even in the cold of space. It's possible. The math works, but it requires special conditions, an unusual origin, an object from the coldest regions of another star system, something that formed differently than the comets we know, different than anything we've directly studied. That's the foundation for what some call the dark comet hypothesis, objects that outgas without creating visible comas, that accelerate without announcement, and that pass through invisibly except for the gravitational and acceleration signatures they leave behind. We're not ready to explore that fully yet. First, we need to sit with this uncertainty, this gap in our knowledge. We know what typical comet outgassing looks like. We know it's visible and detectable. We know Oumuamua didn't show those signs. We know hydrogen could theoretically outgas invisibly. We know hydrogen ice requires conditions we're not sure exist naturally. And we know we can't prove any of this without better data, without catching another object like Oumuamua early, without sending a probe fast enough to reach it before it leaves. The acceleration happened. The numbers don't lie. Something pushed Oumuamua off a pure gravitational trajectory. But whether that something was hydrogen ice or something else entirely remains an open question. One we're still trying to answer with incomplete information and assumptions we can't verify. The invisible wind might be real, or it might be wishful thinking, a convenient explanation for an inconvenient measurement. We're trying to see smoke that might not produce any. We're trying to see smoke that might not produce any. That's where we are with the hydrogen ice hypothesis, a plausible explanation that requires conditions we can't confirm and processes we've never witnessed. Which brings us to something else entirely, a proposal that came not from planetary science or comet research, but from an astronomer who decided to ask a different question entirely. In 2018, Avi Loeb published a paper in the astrophysical journal Letters. Loeb is a Harvard astronomer, chair of the astronomy department, someone with credentials and a reputation. His paper proposed something that made headlines around the world and divided the scientific community, that Oumuamua might not be a natural object at all, that it could be artificial, a light sail, technology. The concept itself isn't science fiction. A light sail is real physics. It's an extremely thin reflective surface pushed by radiation pressure. Photons from sunlight hit the reflective material and transfer momentum. Tiny amounts of momentum, but continuous, unending, like a sailboat on Earth, except instead of wind, molecules hitting the sail, you have photons, light particles, hitting a reflective surface. The force is minuscule, but it doesn't require fuel. It doesn't require outgassing. It just requires light. The thinness required for this to work would be extraordinary. Fractions of a millimeter. Think aluminum foil, but larger than a football field. Imagine a solar panel the size of several city blocks, but thin enough to see through, almost gossamer. A membrane stretched across space. That kind of structure would have an extremely high area-to-mass ratio, a lot of surface for very little mass, which means radiation pressure would have a much larger effect than it would on a solid rock. That would explain the acceleration. No outgassing required. No hydrogen ice required. No visible coma required. Just photons pushing against a thin reflective surface, creating exactly the kind of non-gravitational acceleration we measured. The numbers would work. The physics would work. The explanation would be clean and elegant and would require only one assumption. That assumption being that someone built it. Loeb's argument wasn't based on wild speculation. It was based on the observations. The acceleration without outgassing. The unusual shape, which suggested something with extreme dimensions. The way it tumbled as it moved. A thin, flat object would tumble exactly like Oumuamua tumbled. A dense, elongated rock probably wouldn't. He wasn't saying it was definitely artificial. He was saying we couldn't rule it out, that the artificial hypothesis fit the data as well as any natural hypothesis. Maybe better. The scientific community did not embrace this warmly. Most astronomers rejected it immediately, not because the physics was wrong, the physics was sound, but because the hypothesis violated a principle that guides most scientific thinking. Extraordinary claims require extraordinary evidence, and claiming Oumuamua was artificial technology was about as extraordinary as claims get. The evidence, while unusual, wasn't extraordinary. It was just unexplained. There's also this. The light sail hypothesis doesn't require Oumuamua to be an active, piloted spacecraft. It could be debris, a broken piece of alien technology launched millions of years ago and now tumbling through space with no power, no control, no crew. It could be a defunct probe, ancient garbage, cosmic litter from a civilization that might not even exist anymore. The alien hypothesis might just be trash, not a visitor, not a scout, just the discarded remnant of something that served its purpose eons ago and was left to drift. Now think about that for a second. If Loeb is right, we didn't encounter alien intelligence. We encountered alien refuse. The first confirmed object from beyond our solar system might be the interstellar equivalent of a broken satellite. That reframes the whole conversation. It's not about contact or communication. It's about archaeology, about finding artifacts we can't study, and technology we can't understand, and evidence that someone, somewhere, built things that lasted long enough to cross the galaxy, even if those things are now just fragments, wreckage, the cosmic equivalent of finding a rusted nail in the woods and realizing someone once built a house here. We're investigating a murder mystery where the body has left the building has been demolished, and the city has been paved over. Yet we're trying to solve something that's already gone and can never be examined again. Oumuamua is currently beyond Neptune, moving at 87,000 kilometers per hour relative to the Sun. That's about 54,000 miles per hour, fast enough to circle the Earth in less than an hour. It's not slowing down. It's not coming back. Every second it gets farther away, and with it goes any chance of verification. Loeb's hypothesis explains the acceleration. It explains the lack of outgassing. It explains the shape. It even explains why we've never seen anything like Oumuamua before, because natural processes don't create large-scale, thin, reflective sheets. There's no known geological or chemical process that would produce something with that geometry. If it's a light sail, artificial manufacture is the only option. So the paper was peer-reviewed, published in a legitimate journal. Loeb isn't a fringe scientist. He's not promoting conspiracy theories. He's making an argument based on the data we have and the explanations we've considered. He's saying that when you eliminate the impossible, whatever remains, however improbable, must be considered, even if what remains is technology from another civilization. But here's the problem. The light sail hypothesis does explain the observations. It fits the data. It accounts for the acceleration without requiring invisible hydrogen ice or outgassing we couldn't detect. It's internally consistent, but is it the simplest explanation? Is it more likely that Oumuamua is a piece of alien technology than a comet made of materials we haven't seen before? Is it more probable that we encountered the one artificial object drifting through interstellar space than one of countless natural objects we just don't understand yet? That's the controversy. Not whether the hypothesis is possible, but whether it's probable. Whether it's the explanation we should reach for when natural explanations still exist. When we know comets can behave strangely. When we know our data was limited. When we know we've only been watching for interstellar objects for a few years and have a sample size of exactly 2. The universe doesn't care what we find convenient. It doesn't present itself in ways that fit our existing models. Oumuamua defied expectations because our expectations were built on solar system objects, on comets and asteroids that formed here, from the same materials, under the same conditions. Yet Oumuamua came from somewhere else, from a system with different chemistry, different temperatures, different formation processes. Maybe it looks strange because it is strange, naturally strange, not artificially strange. Or maybe Loeb is right. Maybe we're so committed to natural explanations that we're ignoring the one explanation that actually fits. Maybe the razor cuts the other way. Maybe the simplest explanation for an object that doesn't behave like any natural object we've ever seen is that it isn't natural. We can't know, not without better data, not without catching another object like this earlier, tracking it longer, getting spectroscopy, measuring its composition, not without seeing whether Oumuamua is unique or whether interstellar space is full of objects that accelerate without outgassing. Yet the light sail hypothesis remains on the table, controversial, provocative, unproven, but not disproven either. The honest truth is that we can't get to Oumuamua, not with anything we have, not with anything we're building. The numbers make that clear. But let's walk through them anyway. Let's do the arithmetic of goodbye. Right now, Oumuamua is about 6 billion kilometers away from us. It's moving away at 26 kilometers per second. That's 87 times the speed of sound. Every second, it gets another 26 kilometers farther from where we are. Every hour, it opens the gap by another 93,600 kilometers. The distance grows while we talk about it. So what would it take to reach it? Let's start with the slowest option, walking. Our typical human walking speed is about 5 kilometers per hour. Steady pace. Nothing heroic. At that speed, reaching Oumuamua's current position would take you about 137,000 years. That's not accounting for it moving farther away. That's just to reach the spot where it is right now, as if it were frozen in place, waiting for you. 137,000 years. If you started walking when the last ice age ended, when glaciers covered half of North America and humans were just figuring out agriculture, you would arrive at Oumuamua just about now. Except Oumuamua wouldn't be there. While you walked for 137,000 years, it would have moved another 20 billion kilometers away. You'd arrive at empty space, Nothing but the memory of where it used to be. Maybe walking isn't fair. Let's drive. Put Oumuamua at the end of a very long highway. Get in a car and drive at 100 kilometers per hour. Never stop, never sleep, never slow down for traffic or weather, or the fact that there are no roads in space. At highway speed, you'd reach Oumuamua's current position in about 6,850 years. 6,850 years is longer than recorded human history. The entire span from the first Sumerian writing to smartphones would pass. You'd start driving before the pyramids were built. You'd pass the rise and fall of Egypt, Greece, Rome, every empire that ever existed. You'd still be driving when the printing press was invented, still driving through the Industrial Revolution, still driving past the moon landing, and when you finally arrived, 6,850 years later, Oumuamua would be gone. Moved on. You'd still be chasing. Fine, let's fly. A commercial jet travels at about 900 kilometers per hour, fast enough to cross an ocean in hours. At jet speed, reaching Oumuamua's current position would take 760 years. 760 years is 30 human generations. You'd board the plane before the Renaissance. Your descendants would still be flying when we colonized Mars. And still, Oumuamua would be somewhere else by the time you arrived. None of these speeds are real options: walking, driving, flying. These are Earth speeds. This is an interstellar problem. We need spacecraft. We need the fastest things humanity has ever built. The fastest spacecraft ever launched is New Horizons, the probe that flew past Pluto. It left Earth at 16.26 kilometers per second, screaming fast by any human measure. A bullet travels at less than 1 kilometer per second. New Horizons moves 16 times faster than that. At New Horizons speed, you could reach Oumuamua's current position in about 11.7 years. Launch today, arrive in 2036. That's not a lifetime. That's barely a career. That sounds almost reasonable. Except it isn't, because Oumuamua isn't waiting at that spot. While New Horizons travels 11.7 years to where Oumuamua is now, Oumuamua keeps moving. It's like chasing a train that left the station 6 years ago and never stops. You're running toward where it was, but it's already somewhere else. By the time New Horizons reached the 6 billion kilometer mark, Oumuamua would be 9 billion kilometers away, still receding, still out of reach. What about Voyager 1, the probe that's been traveling since 1977? Now, the most distant human-made object. Voyager 1 currently moves at about 17 kilometers per second relative to the Sun, slightly faster than New Horizons. At Voyager speed, you'd reach Oumuamua's current position in about 11.2 years, barely better. Same problem. By the time you arrive, it's gone. And here's the piece that makes all of this impossible. New Horizons at 16.26 kilometers per second is slower than Oumuamua's escape velocity. Oumuamua is moving at 26 kilometers per second. The fastest spacecraft we've ever launched is almost 10 kilometers per second slower than the object it's chasing. Even if Oumuamua stopped moving right now, froze in place and waited, New Horizons would still be losing ground. We've never built anything fast enough to catch up to it, not even close. This is what goodbye looks like in space. Not a dramatic exit. Just math, just velocity and distance compounding over time. You can run the numbers with any speed you want. Walking, driving, flying, the fastest rocket ever built. The answer is always the same. Too slow, too far, too late. Oumuamua is leaving, and we have no way to follow. Every second, it gets 26 kilometers farther away. While you read this sentence, it traveled 130 kilometers. By the time you finish this paragraph, it's moved another 500 kilometers into the dark. The gap widens, the numbers grow, and the object that gave us questions we can't answer is becoming an object we can't even theoretically reach. We're watching something leave the solar system forever, and all we can do is watch. The fastest things we've ever made aren't fast enough. The furthest we've ever sent anything isn't far enough. Oumuamua came from somewhere out there in the galaxy, stayed for a few months, and now it's going back, and we're standing still, relatively speaking, watching it go. Let's try to count to 6 billion, one number per second. No breaks, no sleep, no stopping to eat or breathe or rest. Just counting. 1, 2, 3, 4, all the way to 6 billion. It would take you 190 years. You'd start counting as a newborn. Keep counting through childhood, through school, through your entire adult life. Yet you'd count through your retirement, through old age, and you'd die somewhere around number 3 billion, not even halfway there. Your children would have to keep counting. Their children too. 3 full human lifetimes of continuous counting, every second of every day, just to reach the number of kilometers between us and Oumuamua right now. Right now. Not when it arrived, not when we first saw it. Right now, as you're hearing this. And it's still moving. Here's another way to think about it. Your heart beats roughly 100,000 times per day. Over an average lifetime, that's about 2.5 billion heartbeats. Every moment of your life, from your first breath to your last, measured in heartbeats. 2.5 billion of them. That's not enough to count the distance to Oumuamua. You'd need to live twice. And consider this. If every human heartbeat since the first Homo sapiens walked on Earth was a kilometer, you'd reach Oumuamua's current distance and still have 1 billion heartbeats left over, each one a kilometer of emptiness. Every pulse of every human who ever hunted, who ever built fire, who ever looked up at the stars and wondered. All those heartbeats, all those lives. And Oumuamua is farther than that. The light leaving Oumuamua right now, if we could somehow see it, takes 5.5 hours to reach us. 5.5 hours traveling at the fastest speed possible in the universe. And in those 5.5 hours, while that light is crossing the void between there and here, Oumuamua moves another 515,000 kilometers farther away. We can't see where it is. We can only see where it was. And by the time we see that, it's somewhere else. There are roughly 8 billion people alive on Earth right now. 8 billion individual humans, each with their own life, their own thoughts, their own heartbeats counting down. That's more people than have ever existed at one time in human history. There are fewer people alive than there are kilometers to Oumuamua, but not by much. Every human who ever lived, though, every person who was ever born, who ever died, who ever existed in all of human history, best estimates put that number at 117 billion people, from the first humans in Africa to everyone alive today. 117 billion lives. That's roughly 20 times the current distance to Oumuamua in kilometers. 20 times 6 billion. Every ancestor you ever had. Every stranger who walked the earth before you. Every life that led to your life. Multiply all of that by 20, and you get the distance to one object leaving our solar system. I think about this sometimes. Not the numbers themselves. The numbers are just numbers. But what they mean, that something visited us, came from somewhere else. Somewhere we'll never see, never reach, never know. And it's leaving. Already left, really. And every single second, it gets farther away. And it will never, ever stop. Not in your lifetime. Not in your children's lifetime. Not in the lifetime of our civilization. If we even survive that long. If you counted 1 kilometer for every day since Stonehenge was built, you'd still be counting today. Stonehenge is roughly 5,000 years old. That's about 1.8 million days. Yet you'd need to go back 3 million more days to reach 6 billion. Back past the pyramids, past the first cities, past the invention of agriculture. Count 1 kilometer for every day of recorded human history, and you'd still be counting when your grandchildren die. The distance isn't just big, it's historically big, generationally big. It's bigger than civilizations, and it keeps growing. If you counted 1 kilometer per second since the day you were born without sleeping, you still wouldn't reach Oumuamua's current distance by the time you retire. And that's if you started counting the moment you were born and never stopped. 65 years of counting, 1 number per second, 24 hours a day. That gets you to about 2 billion. You'd die at 80 having never reached 3 billion. Yet you'd need to live 200 years, counting constantly, to measure the emptiness between here and there. No human has ever lived that long. No human ever will, probably. The object is unreachable in ways that go beyond engineering, beyond technology. It's unreachable in human terms, in lifetime terms, in the fundamental units we use to measure our existence. Heartbeats, breaths, days, years, lifetimes. Not enough. None of it is enough. There's something almost cruel about it. That Oumuamua came close enough for us to see, close enough to study, close enough to wonder about, and then it left. And the distance between us and it is measured now in billions, in numbers so large they don't fit inside a human life. The light from Oumuamua's current position, if you could see it, had left before you finished reading this sentence. Actually, that's not quite right. You're not reading, you're listening. Before you finished hearing this sentence, the light left, traveled at the speed of light for 5.5 hours, and by the time it arrives here, Oumuamua will be 500,000 kilometers farther along its journey. We're not looking at where it is. We're looking at where it was. A ghost, an echo, and the real object, the actual physical thing that passed through our solar system, is already gone, already somewhere else, already beyond the numbers we just counted. Every attempt to measure the distance is obsolete before we finish stating it. 6 billion kilometers. Except, it's not 6 billion anymore. It's 6 billion and 26 more. 6 billion and 52. 6 billion and 78. The number changes faster than we can speak it. That's what goodbye looks like at this scale. Not a moment, not an event, just a number that grows and never stops growing. We're counting to infinity, and Oumuamua is already there. So how do you confirm that a tumbling rock, millions of kilometers away, moving faster than anything you've ever tracked, isn't coming back? How do you prove it's an interloper and not just a very lost member of our solar system? You measure it, again and again and again. You track its position against the stars with the kind of precision that makes your eyes water just thinking about it. This is astrometry, the art of measuring where something is in the sky. Exactly. Not approximately. Not close enough. Exactly. A measuring position to within fractions of an arcsecond is like spotting a quarter in Los Angeles from San Francisco with your naked eye. That's the level of accuracy required. Astronomers photograph Oumuamua against the background of distant stars. Stars so far away, they don't appear to move. Those stars become the reference grid, the fixed points. And against that grid, Oumuamua slides. Each observation captures a single moment, a point in space and time. One photograph shows Oumuamua here, relative to those background stars. 6 hours later, another photograph shows it there, then there, then there. Each point is a breadcrumb. Each breadcrumb traces a path. String enough points together, and you don't just have positions anymore. You have motion. You have an arc. That arc is everything. And it tells you not just where Oumuamua went, but where it came from. It tells you how fast it's moving and in what direction. It tells you whether gravity is the only force acting on it. And most importantly, it tells you whether this thing is ours or not, whether it's bound to the sun, destined to swing back someday, or whether it's just passing through, a visitor, one and done. The mathematics of orbits are old. Kepler figured out the basic rules 400 years ago. Objects orbit in ellipses if they're bound to the sun, in parabolas or hyperbolas if they're not. The shape of the orbit depends on a single number called eccentricity. That number tells you everything. An eccentricity of 0 means a perfect circle. Between 0 and 1 means an ellipse, stretched to varying degrees. The closer to 1, the more stretched. 1 exactly means a parabola, the boundary case between bound and unbound. Anything above 1 means a hyperbola, and a hyperbola means escape. Think of eccentricity as measuring how stretched an orbit is. A circle has no stretch. It's 0. An ellipse has some stretch, somewhere between 0 and 1. But anything above 1 means the object isn't coming back, period. It's the mathematical difference between a swing and a throw. A swing returns to your hand. A throw keeps going. Oumuamua was thrown. But here's what most people don't realize. The hyperbolic trajectory wasn't confirmed immediately. When astronomers first spotted Oumuamua, they had only a handful of observations. A few points along the arc, early orbital calculations showed an eccentricity close to 1. Very close. Maybe 1.03, and maybe 1.07. The error bars were large. There was genuine uncertainty about whether this might be a highly elliptical orbit that would eventually, millions of years from now, bring Oumuamua back. For a brief moment, astronomers considered it might be a very long-period comet on a return visit, something that had been here before, eons ago, swinging through on another pass. We almost thought it was ours. More observations came in. Telescopes around the world swung toward this faint moving dot. Each new data point tightened the arc. Each new measurement refined the eccentricity calculation. 1.1, then 1.15, then 1.19. The number climbed, the error bars shrank, and at some point, days after discovery, the value solidified above 1.0, definitively. Yet the final figure settled around 1.2. No ambiguity, no room for interpretation. Oumuamua's orbit was hyperbolic. It came from somewhere else. It's going somewhere else. This solar system is just a brief moment in between. Eccentricity alone doesn't tell you velocity, but the two are connected. At Earth's distance from the Sun, the escape velocity is 42 kilometers per second. That's how fast you'd need to throw something for it to leave the solar system forever, never to return. 42 kilometers per second. That's fast enough to circle the Earth in about 16 minutes. Oumuamua's velocity at Earth's distance exceeded that threshold, not by a little. It was moving faster than escape velocity when it passed through our neighborhood. Gravity couldn't hold it. Working backward from the trajectory, astronomers calculated Oumuamua's incoming velocity from interstellar space before the Sun's gravity sped it up, about 26 kilometers per second. That's its natural cruising speed, the speed it had in the void between stars. For reference, the Sun orbits the center of the Milky Way at about 230 kilometers per second. Oumuamua was moving at roughly a tenth of that, not fast by galactic standards, just drifting, really. Drifting until it happened to pass close enough to our Sun to get pulled inward, slingshot around, and flung back out the other side. The trajectory always points backward in space. You can trace the arc in reverse, following it back through the years, through the centuries, through the millennia. Where did it come from? The calculations suggest a direction in the sky near the star Vega, in the constellation Lyra, near Vega, not from Vega. Because here's the thing, Vega wasn't in that part of the sky 300,000 years ago. Stars move, the galaxy rotates, everything is in motion. By the time you trace Oumuamua's path back far enough to find its origin, the stars have rearranged themselves. Vega is just the current landmark near the direction it came from. The actual source, the actual star system it might have originated from, is unknown. Could be any of thousands of candidates. Could be a star we've never even catalogued. That's how precise the measurements are. We can calculate a trajectory backward through 300,000 years of travel. We can determine an eccentricity to 2 decimal places. We can measure a velocity to within fractions of a kilometer per second. And yet, we still don't know where it came from. The precision is staggering. The ignorance remains. This level of accuracy cuts both ways. It's the same precision that confirmed the hyperbolic trajectory that also detected something else, something strange, a tiny, persistent acceleration that couldn't be explained by gravity alone. Throwing a baseball from New York and having it curve slightly left by the time it reaches London, then arguing about whether air resistance or quantum tunneling caused the curve. That's the precision required to detect the acceleration anomaly. Not an approximation, not a guess, a measurement. Multiple telescopes, multiple observations, multiple teams checking the math. The acceleration is real. These are not rough estimates. These are not ballpark figures. Every number comes from careful observation, from photographs analyzed down to the pixel, from equations tested and retested. When scientists say Oumuamua's eccentricity is 1.2, they mean 1.2. When they say it's accelerating, they mean it's accelerating. The confidence isn't arrogance. It's math. Cold, precise, unforgiving math. The kind that doesn't care what you believe or what you want to be true. The orbit is hyperbolic. The object came from interstellar space. It's leaving and never coming back. Those are facts, measured facts. And that same rigor, that same methodological obsession with accuracy, now has to grapple with the acceleration. Something pushed Oumuamua slightly off course. Something subtle enough that it almost went unnoticed, but real enough that it shows up in the data no matter how many times you recalculate. The mystery isn't whether the acceleration happened. The mystery is what caused it. The measurement is solid. The interpretation is where things get messy. The measurement is solid. The interpretation is where things get messy. Because while scientists were wrestling with what pushed Oumuamua off course, something unexpected happened. They found similar objects right here in our own solar system. Objects that shouldn't exist according to everything we thought we knew about asteroids and comets. Objects that behave like Oumuamua. Objects that accelerate without announcing themselves. Astronomers have a habit of calling things dark when they can't see them. Dark matter, dark energy, dark comets. It's like a cosmic admission of failure. We know something's there because of what it does, but we can't see it. And so we just put dark in front and call it a day. It's the astronomical equivalent of shrugging. But dark comets are real, and they might explain everything. Here's what a dark comet is. It's an object that accelerates like a comet, pushed by outgassing, but shows no visible coma, no tail, no cloud of gas and dust glowing in the sunlight. The acceleration is there. The signature of outgassing is unmistakable in the trajectory, but the visual evidence, the thing that makes a comet look like a comet, is completely absent. A dark comet is to a normal comet what a ninja is to a person wearing bells. Same thing, different visibility. The first potential examples were identified in 2023. Several near-Earth asteroids, objects that had been observed for years, showed unexplained trajectory deviations. Tiny deviations, the kind you'd only notice if you were tracking their orbits with obsessive precision. The kind that match exactly what you'd expect from outgassing. These weren't measurement errors. Multiple observations confirmed it. The objects were accelerating, just slightly, in ways gravity alone couldn't explain. But they looked like asteroids. Dark, inert, no coma, no tail, nothing. Finding dark comets in our own solar system is like discovering your neighbor has been invisible the whole time, walking past you every day, yet you only notice when their footprints appear in snow. We didn't see them. We saw their effects. The proposed mechanism is simple. These objects are outgassing volatiles that don't create a visible coma. Maybe molecular hydrogen, maybe nitrogen. Gases that don't reflect much light, that don't form dust particles, that escape into space without making a show of it. The outgassing is real. It's just invisible. And here's the thing. These objects are small, tens to hundreds of meters across. Oumuamua is somewhere between 100 and 400 meters long, depending on its shape. At that scale, even if there's outgassing, the coma would be incredibly faint, maybe too faint to detect with our telescopes. Maybe there, but invisible against the background of space. If every person who ever lived stood single file, and the line would stretch to the moon and back 30 times. Dark comets are more invisible than the gaps between those people. They're there, they're real, but they don't announce themselves. The timeline here is striking. Oumuamua was discovered in October 2017. The first potential dark comets in our solar system were identified 6 years later, in 2023. That's not a coincidence. Oumuamua made astronomers look more carefully at trajectory anomalies. It made them question whether other objects might be doing the same thing on a smaller, subtler scale. We discovered potential dark comets in our own solar system after Oumuamua's discovery, partly because Oumuamua made us realize we should be looking for them. Oumuamua wasn't the only mystery, and it was the first mystery that made us realize there might be a whole class of mysterious objects we'd been ignoring. It wasn't an anomaly, it was the beginning of a pattern. Think about that for a second. We spent decades cataloging asteroids, tracking their orbits, confident we understood the difference between asteroids and comets. Then, Oumuamua shows up, accelerates without a visible coma, and everyone scrambles for an explanation. And in the scrambling, in the careful re-examination of data we already had, we find that our own solar system contains objects doing the exact same thing. We just hadn't noticed because we weren't looking. The dark comet hypothesis fits Oumuamua perfectly. It explains the acceleration without invoking alien technology or exotic physics. It proposes a natural mechanism, an outgassing of volatiles like hydrogen or nitrogen that leaves no visible trace. It accounts for the lack of a coma even with outgassing, and critically, it's consistent with objects we've now found in our own solar system. If dark comets exist here, among the near-Earth asteroids we've been tracking for years, then interstellar dark comets should also exist. There's no reason to think our solar system is special. If comets can be dark here, they can be dark anywhere. An interstellar dark comet passing through our solar system wouldn't be weird. It would be expected. The hypothesis has been published in Icarus and other peer-reviewed journals. It's a serious contender, a naturalistic explanation competing directly with the light sail theory. It doesn't require advanced civilizations or deliberate construction, and it just requires that comets sometimes outgas materials we can't easily see, which is simpler, that Oumuamua is a type of object we've now found evidence for in our own solar system, or that it's a piece of alien technology. Occam's razor would suggest the former. The simplest explanation that fits the data is usually correct. Dark comets are simple. They're comets behaving like comets, just without the visual fanfare we're used to. But here's where it gets complicated. We don't have definitive proof that the near-Earth objects showing these trajectory anomalies are actually outgassing. We infer it from the acceleration. We propose mechanisms that would make the outgassing invisible, but we haven't directly detected the gas. We haven't sampled it. We've seen the footprints, but we haven't seen the person. And the same is true for Oumuamua. The dark comet hypothesis explains the acceleration. It fits the data, but we don't have direct evidence of outgassing. We have an explanation that works, but we can't confirm it. Both hypotheses, the light sail and the dark comet, remain on the table. Both fit the observations. Both require assumptions. The light sail requires advanced alien civilizations. The dark comet requires that outgassing can be invisible under certain conditions. Which assumption you find more reasonable depends on how you weigh the probabilities. The universe doesn't care what we find convenient. It doesn't care which explanation we prefer. The truth is whatever it is, regardless of our theories. What we know for certain is this. Oumuamua accelerated. It came from interstellar space. It showed no visible coma. And now we've found objects in our own solar system that seem to do the same thing. That's the pattern. That's what the data tells us. The interpretation is still being written. The interpretation is still being written. That's where we left Oumuamua, with questions, not answers, with possibilities, not certainty. But here's the thing. Oumuamua was never just about one object. It was about opening a door we didn't know was there. We've spent thousands of years looking up at the night sky. We've catalogued stars. We've mapped galaxies. We've found planets around distant suns. But until October of 2017, we'd never detected a single object passing through from another star system. Not one. In all of human history, our census of interstellar visitors was 0. Then it was 1. And soon, it will be dozens. The Vera C. Rubin Observatory is about to change everything. This telescope, currently being completed in Chile, represents a fundamental shift in how we watch the sky. It's expected to begin operations in late 2025. What makes it different isn't just size or sensitivity, it's speed. The Rubin Observatory will survey the entire visible sky every few nights. Every few nights, the whole sky. It will photograph billions of objects, track them, compare them to previous images, and flag anything that moves in an unexpected way. Think about what that means. Trying to photograph a ninja in a dark room with a camera that takes 1 picture per month. That was the state of astronomy before Rubin Observatory. Now we're about to install floodlights and high-speed cameras. The ninja won't be able to hide anymore. Neither will interstellar objects. Current predictions suggest the Rubin Observatory will detect between 1 and 70 interstellar objects per year. The range is wide because the models disagree. We don't know how common these objects actually are. We have a sample size of 2, Oumuamua and Borisov. That's not enough data to build reliable statistics. But even the conservative estimate, 1 object per year, represents a revolution. All of human astronomy before 2017 detected 0. We're going from complete ignorance to statistical surveys in less than a decade. 1 per year sounds small, maybe even disappointing, but consider what it means. Every year we'll get another chance, another object to study, another data point. 1 object is an anecdote, dozens is data. We'll be able to compare them, look for patterns, or ask questions we couldn't ask before. Are they mostly rocky? Mostly icy? Do they all accelerate? Do they all tumble? Are there common shapes, common sizes, common behaviors? We'll learn what's typical and what's strange. We'll finally understand what Oumuamua actually was, not by studying Oumuamua itself, but by seeing what else is out there. And here's the surprise, the real shock hiding in the models. Current estimates suggest that interstellar objects may pass through the inner solar system once every few months, not once per century, once per season. They've been coming this whole time, silent, unnoticed, passing between the planets while we looked right past them. We weren't seeing them not because they're rare, but because we weren't looking carefully enough. The galaxy may be full of debris, fragments from planetary formation, ejecta from asteroid collisions, rocks flung out of their home systems by gravitational interactions, comets kicked loose by migrating giant planets. They're wandering, drifting between the stars, and sometimes they pass through our neighborhood. They always have been. We just never noticed. We were reading by candlelight, and we missed most of the library. If interstellar objects are rare books in a library, we've been searching with a candle. We found 1 book, Oumuamua, by accident. Soon we'll turn on the lights and realize the library has hundreds of volumes we never saw, shelves and shelves of them. Each one a story from another part of the galaxy, each one carrying information about a star system we'll never visit, the chemistry of distant worlds, the violence of planetary formation, and the diversity of objects that exist out there in the dark. The next visitor might be detected earlier. That's the hope. Oumuamua was already on its way out when we spotted it. We had weeks, not months. We scrambled. We pointed every available telescope at it, but we didn't have time for everything we wanted to do. Spectroscopy to analyze surface composition, polarimetry to study light reflection, radar observations to measure rotation and shape directly. We got some data, not enough. The next one could be different. If we catch an object on its way in, we'll have months, maybe longer. Time to plan, time to coordinate, time to use every tool we have. We could study it across multiple wavelengths, track its rotation precisely, measure its outgassing, if it has any, search for surface features, composition variations, as structural details. We could answer questions about Oumuamua by studying its cousins, its siblings, the family of objects we now know exists. Better preparation matters. When Oumuamua appeared, we were surprised. We had no protocols, no observation plans ready, no coordinated international response. We improvised, and we did well, but we could do better. Now we know they're coming. Observatories are preparing. Astronomers are writing response plans. When the next interstellar object appears, we won't be starting from scratch. We'll be ready, and we'll learn, not just about the objects themselves, but about the galaxy they come from. Every interstellar visitor is a sample, a tiny piece of a star system light years away, delivered to our doorstep. We can't send probes to those systems. We can't visit them. But we can study what they send us, the rocks they lose, the debris they eject, the fragments that drift into interstellar space and eventually pass through ours. Each object is a message. We just have to learn how to read it. Oumuamua raised more questions than it answered. That's true, but it proved something profound. It proved we could detect these objects. It proved they exist. It proved they visit. That's not a small thing. Before October of 2017, interstellar objects were theoretical, predicted by models, but never seen. We had no proof. Now we do. And soon, we'll have more than proof. We'll have a catalogue, a data set, a population to study. The future looks different now, not because Oumuamua answered our questions, because it showed us what questions to ask. How common are interstellar objects? What are they made of? Where do they come from? How long have they been wandering? Do they cluster in certain regions of the galaxy? Do they favor certain trajectories? These questions didn't exist before 2017. Now, they define a field of study, interstellar object science, a discipline born from one unexpected visitor. We're standing at the beginning. The Rubin Observatory will start surveying soon. The objects will come. We'll detect them, study them, learn from them. What we discover might surprise us. It probably will. The universe doesn't care what we expect. It just is. And we're finally developing the tools to see what's actually there. Not what we think should be there. What is. Oumuamua was the first. It won't be the last. That's the message. That's the meaning. We're not alone in the galaxy. And not in the way we usually think about that phrase, but in a different sense. We share this galaxy with countless objects, wanderers from other stars, visitors we never noticed. They've been passing through this entire time, silent travelers on journeys that span millions of years. Now, finally, we can see them, we can study them, we can learn what they have to teach us about the galaxy we all inhabit. The question isn't whether more will come. They will. The question is what we'll do when they arrive. The question is whether more will come. That's settled. They will. But here's the other question, the harder one. Can we catch one? Oumuamua is gone. It passed its closest point to Earth in October 2017. By the time we understood what we were looking at, it was already leaving, racing away at more than 26 kilometers per second. That's 94,000 kilometers per hour, fast enough to cross the entire continental United States in about 40 seconds. And it's still accelerating away. Every day it gets farther. Every day the gap widens. The natural human impulse is to chase it, to send something after it, a probe, a camera, anything that could get close enough to see what it actually is. Scientists felt this too. The moment Oumuamua was confirmed as interstellar, proposals started appearing. Mission concepts, trajectory studies, launch windows. The question wasn't whether we wanted to. The question was whether we could. The answer surprised people. Theoretically, yes, we could catch it. There's a project, a theoretical study called Project Lyra, proposed by the Initiative for Interstellar Studies. It's not a funded mission, not a spacecraft sitting in a clean room somewhere. It's a collection of papers, calculations, orbital mechanics pushed to their limits. The researchers asked a simple question. If we wanted to intercept Oumuamua, what would it take? The answer involves some of the most complex maneuvers we know how to perform. Chaining together gravity assists, threading trajectories through the inner solar system, using the sun itself as a gravitational slingshot. It's like a relay race where the first runner hands off the baton to someone standing on the moon, who hands it to someone on Mars. That's the complexity of chaining gravity assists and Oberth maneuvers to catch something moving this fast. Every step has to be perfect, every calculation exact. One mistake and you miss by millions of kilometers. Let's start with the launch window. The optimal time is between 2030 and 2033. That's soon, just a few years away. The reason is geometry, where the planets will be, where Oumuamua will be, where the sun sits in relation to everything else. These alignments don't last. Miss the window and you wait decades for another chance. Or you accept a much harder trajectory, one that requires more fuel, more time, more risk. The mission would use a Jupiter gravity assist. The spacecraft launches from Earth, heads toward Jupiter, swings around the giant planet and steals some of its orbital momentum. This isn't new. We've done it before. Voyager did it. New Horizons did it. You approach a planet moving one speed. You leave moving another, faster. And the planet slows down infinitesimally. You speed up enormously. Physics conserves momentum. You just borrow some from something bigger. But Jupiter alone isn't enough. Not for this. Oumuamua is moving too fast. You need something more extreme. Something called a solar Oberth maneuver. Here's how it works. After the Jupiter assist, the spacecraft dives toward the Sun. Close. Dangerously close. Within a few million kilometers of the surface. For reference, Mercury orbits at about 58 million kilometers. This trajectory goes much closer, close enough that the spacecraft is falling, accelerating, gaining speed from the Sun's gravity, and then, at the lowest point, at perihelion, the spacecraft fires its engines. This is where it gets strange, as diving close to the Sun to gain speed is like a skateboarder dropping into a halfpipe. The deeper you go, the faster you climb out the other side. But instead of falling 6 feet, you're falling toward an object 1.4 million kilometers wide and hotter than a nuclear bomb. The spacecraft isn't just moving fast at perihelion, it's moving incredibly fast, and that's when the engines fire. The Oberth effect means firing your engines deep in the Sun's gravity well gives you more speed than firing the same engines in deep space, because your kinetic energy adds to your potential energy more efficiently at high speed. It's not intuitive. The same engine, the same fuel, produces more velocity change when you're already moving fast near a massive object. Physics rewards risk. Think about it this way. And if you're standing still and you throw a ball, it goes a certain distance. If you're on a moving train and you throw the same ball in the direction the train is moving, it goes farther. Same arm, same throw, different result. The Oberth effect is similar, but with rocket engines and gravity wells. You add velocity when you're already at high velocity, and the multiplication effect is enormous. Using this maneuver, a spacecraft could achieve speeds of 70 to 100 kilometers per second. That's faster than anything we've ever built. Faster than Voyager, faster than New Horizons, faster than the Parker Solar Probe, which currently holds the record. You'd be moving at 1/3000th the speed of light, which sounds small, but it's not. It's ridiculously fast by human standards. Now, if you launched in the early 2030s, intercept would happen around 2048 to 2050. That's 17 to 18 years of flight time. Launching in the early 2030s to intercept in 2048 means starting a mission today whose success your children might witness, and gambling billions on the answer being worth it. You'd design the spacecraft now, build it in the 2020s, launch it in the early 30s, and wait, nearly 2 decades, hoping nothing breaks, hoping the calculations were right, hoping the object you're chasing is still interesting when you arrive. And there's no guarantee it would be. Oumuamua might be exactly what the mainstream scientists think: a rock, a comet without a tail, a chunk of nitrogen ice from a distant planetary system. Interesting scientifically, sure, but worth billions of dollars, worth decades of effort? That's harder to justify. The propulsion requirements are severe. You'd need either high-thrust chemical rockets, which means enormous fuel mass, or nuclear electric propulsion, which we haven't fully developed yet. Nuclear electric systems are efficient. They provide thrust for months or years instead of minutes. But they're complex, heavy, expensive, and politically difficult. Launching a nuclear reactor into space makes people nervous. The regulations are strict, the testing requirements extensive. Cost estimates for a mission like this run into the billions. Low single-digit billions if everything goes perfectly. Higher if development takes longer than expected, which it always does. For comparison, the Mars Curiosity rover cost about $2.5 billion. The James Webb Space Telescope cost nearly $10 billion. A mission to Oumuamua would sit somewhere in that range, probably closer to Webb than Curiosity, given the propulsion challenges. And for what? A flyby. The spacecraft wouldn't slow down. It couldn't. Slowing down requires even more fuel, more mass, more complexity. At intercept, you'd be screaming past Oumuamua at dozens of kilometers per second, maybe faster, depending on relative velocity vectors. You'd get minutes, maybe an hour if you're lucky, one chance to take pictures, gather data. her measure composition, then it's over. The spacecraft continues on, out of the solar system, into interstellar space. You don't get a second pass. The question isn't just whether we can do it. The question is whether we should. Whether it makes sense to spend that much money chasing one object when more are coming. When the Rubin Observatory will start finding them regularly. When the next interstellar visitor might be closer, slower, easier to study. Project Lyra represents what's possible, the absolute edge of our current capability. But possible doesn't mean practical. The mission would push every system to its limit, require technology that barely exists, demand perfection across decades of operation. And at the end, you might discover that Oumuamua was just a rock, unremarkable except for where it came from. Some scientists argue for it anyway. They say the first of anything is special, that we'd learn things we can't predict, that even if Oumuamua is just a rock, it's a rock from another star, formed in conditions we can only guess at, carrying information about a planetary system we'll never visit. They say the knowledge is worth the cost. Others disagree. They say we should wait, build better telescopes, catch the next one, learn from Oumuamua's detection, and prepare for the next interstellar visitor. They'll keep coming. Some will be easier targets, closer, slower, detected earlier. Why exhaust our resources chasing the one that got away when another might arrive next year? Both arguments have merit. There's no clear answer, just a choice. Chase the mystery now, with all the risk and cost that entails, or wait for better opportunities, for easier targets, for more funding, for clearer science goals. Oumuamua is still out there, still moving, still carrying its secrets into the dark. We could follow it, theoretically. The physics work, the trajectories exist. But whether we will is a different question entirely, one that depends on money, politics, priorities, luck, the things that always decide what humanity reaches for and what it lets slip away. The choice isn't really about Oumuamua anymore. It's about something deeper, something that keeps astronomers awake at night. This is the terrible, captivating irony of modern astronomy. We're good enough now to detect mysteries, but not yet good enough to solve them before they slip away. We see the ghost, but by the time we build the ghost detector, the ghost is gone. And we have to decide, do we chase ghosts or do we wait for the next haunting? The numbers are staggering. The James Webb Space Telescope cost about $10 billion over 25 years. That's enough money to pay 100,000 teachers for a decade. The Mars Sample Return mission carries an estimated price tag between $8 and $11 billion. Project Lyra, the proposed mission to intercept Oumuamua, would cost somewhere in that same range, $10 billion. A decade or more of planning and construction, hundreds of careers, thousands of engineering hours. But here's what people don't understand. The cost of Project Lyra isn't the expensive part, it's the opportunity cost. The question isn't, can we afford this? The question is, what do we not do if we do this? Every spacecraft sent to Oumuamua is a spacecraft not sent to Europa, not sent to Enceladus, not sent to characterize a biosignature-rich exoplanet 40 light-years away. Science funding is finite, brutally finite. Money spent chasing an interstellar visitor is money not spent mapping ocean worlds, not spent searching for life, not spent on the next generation of telescopes that might catch the next Oumuamua earlier, when it's still within reach. We're not just gambling money. We're gambling the future direction of space exploration for the next 2 decades. Picture this. You're investigating a car crash, trying to understand what happened, except the car has already been scrapped, melted down, turned into rebar. That rebar has been poured into the foundation of a building, and you're standing there, trying to decide whether to demolish the entire building to examine the rebar, knowing full well you might learn absolutely nothing. That's the Oumuamua decision. The evidence is gone. Still exists, technically, but retrieving it requires tearing down everything around it. And you won't know if it was worth it until after you've already committed. Some scientists say we have to try. They say the first of anything deserves special attention. That even if Oumuamua turns out to be just a nitrogen iceberg, just a hydrogen shard, just a rock. We'll learn something we can't learn any other way. Formation conditions in another stellar system. Chemical compositions we can't replicate in laboratories. Data about the interstellar medium that no telescope can provide. They say the knowledge justifies the cost, and that some questions demand answers regardless of price. Others say we should wait, be patient, build better detection networks, prepare for the next visitor. Oumuamua won't be the last. Statistically, there should be another interstellar object passing through the inner solar system every few years. Some will be slower, some will be detected earlier when we still have time to mount a proper mission. Some might even be inbound, giving us years of warning instead of weeks. Why exhaust our resources chasing the one that slipped through our fingers when another might arrive before we even finish building the spacecraft? Both arguments have merit. There's no objectively correct answer, just values and priorities and acceptable levels of risk. Consider the gamble another way. If deciding whether to chase Oumuamua is like deciding whether to spend your entire life savings on a lottery ticket that might pay off in 25 years. Except this lottery might teach us about alien technology. It might rewrite everything we know about planetary formation. It might be the most important scientific discovery in human history. Or it might just teach us about space rocks, about dust and ice and ordinary physics. You won't know until you've already spent the money, already committed the time, already chosen this path over all the others. We're standing at a fork in a dark forest. One path leads towards something we've already lost, something that's still moving away, getting harder to reach with every passing day. The other path waits for the next thing to appear. Both paths cost years. Both cost billions. Both demand we sacrifice other possibilities. Choose. This is the reality of modern astronomy. Our capability has outpaced our accessibility. We can detect things we can't study. We can measure things we can't reach. We can ask questions we can't yet answer. The gap between detection and investigation grows wider every year. Our telescopes get better. Our sensors get more sensitive. We find more mysteries. But the infrastructure to investigate those mysteries, the spacecraft, the funding, the institutional will, those don't scale at the same rate. The decision about Oumuamua isn't really about Oumuamua. It's about what kind of science we want to do, what kind of knowledge we prioritize, what risks we're willing to take for understanding. Do we chase every mystery the moment it appears, consequences be damned? Or do we wait for better opportunities, clearer targets, more favorable circumstances? There's no formula for this, no equation that spits out the right answer, just people in rooms, arguing over proposals, politicians deciding where to allocate budgets, scientists advocating for their particular vision of what humanity should reach for next. The same forces that decide everything we do in space: money, politics, priorities, timing, luck. And while we argue, while we debate the merits and costs and philosophical implications, Oumuamua keeps moving, still out there, still carrying whatever secrets it carries, still slipping further from our reach. The window doesn't stay open forever. Every month we delay makes the mission harder, more expensive, more technically demanding. Eventually, the window closes completely. The choice gets made by default, not because we decided no, because we didn't decide yes fast enough. That's the cruelest part. Inaction is a decision. Waiting is a choice. And sometimes, waiting too long means the choice gets made for you. The ghost disappears. The forest path grows over. The opportunity passes. And you're left wondering what you missed, what you might have learned if you'd been just a little braver, a little more willing to gamble, a little less afraid of wasting resources on a question that might not have an answer worth the asking. Oumuamua is gone now, 6 billion kilometers away and getting farther every second, moving at 26 kilometers per second toward the constellation Pegasus. That's roughly 94,000 kilometers per hour, fast enough to circle Earth twice in 1 hour. And it will never slow down. No friction in space to brake against. No gravity strong enough to turn it around. Just constant motion, forever, in one direction, away. It will take Oumuamua 20,000 years to travel just one light year. 20,000 years. That's longer than all of recorded human history. Every pharaoh, every empire, every war, every discovery, every moment we've written down. And at the end of all that time, Oumuamua will have traveled the distance light covers in 1 year. Just one. The nearest star to us after the Sun is 4 light years away. Do the math. Oumuamua isn't going anywhere fast. Not on cosmic scales. In 40,000 years, it will pass within 1.6 light years of a star called Ross 248. That's the closest it will come to anything for a very long time. And here's the thing. In 40,000 years, Earth will still exist. Humans might still exist. Our species might have spread to other stars or vanished entirely, but the planet will be here. And Oumuamua will have been traveling for longer than we've been human, longer than we've had language, longer than we've buried our dead or painted on cave walls, and it still won't have reached another star. Interstellar space isn't empty, it's just unimaginably vast. And somewhere in that vastness right now, Oumuamua is tumbling silently, carrying whatever it is, a comet, a fragment, a piece of ice or rock or something we don't have a name for. We'll never know for certain. The data we have can support multiple explanations, and we'll never get more data. The case stays open. The question stays unanswered. That's not failure. That's just what happened. We detected our first confirmed visitor from another star system. We tracked it. We studied it with every telescope we could point at it. We argued about what it was and what it meant. We proposed missions to chase it down. And now it's leaving, carrying its secrets with it. And there's nothing we can do about that. But we proved something. We proved we can find these objects. We proved they exist, passing through our solar system, coming from places we've never been. We proved our telescopes work, our methods work, our ability to spot something small and dark and fast moving against the infinite black works. The next one we'll be ready for. Maybe not with a mission, maybe not with a spacecraft chasing it down before it escapes, but with better instruments, better preparation, better plans. But we know what to look for now. We know how much time we have. We know what questions to ask. Oumuamua was a test we didn't know we were taking, and we passed. Barely, but we passed. There's an analogy I keep coming back to. We are standing in a dark field, and something just brushed past us in the night. We caught a glimpse, not enough to see clearly, but enough to know it was real. And now we have a choice. We have maybe 30 years to decide whether to chase it into the darkness or wait for the next thing to brush past us. Either way, we now know something we didn't know before. We are not alone in this field. There are others, passing through, just passing through. That's what Oumuamua means. Not as an object, as a moment. The moment we looked up and saw proof that the universe is full of travelers, full of things moving between stars, drifting through the dark, visiting systems that aren't their home. We always suspected it. The math said it should be true, but suspecting something and seeing it are different things. We saw it, and it changed us. Not in some grand, obvious way, but quietly. The way any first time changes you. The first time you see the ocean. The first time you leave your home country. The first time you realize the world is bigger than you thought. Oumuamua was our first interstellar visitor. There will be others, maybe dozens in our lifetime, maybe hundreds as our telescopes improve. But there's only ever one first. This was ours. It's gone now, beyond our reach, beyond our ability to study or chase or understand, tumbling through the dark between stars, heading nowhere in particular, and going nowhere fast. It will outlast us, outlast our civilization, outlast our species, probably, outlast the sun, maybe, just a piece of rock or ice, spinning silently, forever. And we were here to see it pass. If you want to follow more stories like this, more moments where we catch glimpses of the universe doing something unexpected, subscribe. There are more visitors coming, more mysteries, more objects that don't fit our models and don't answer our questions neatly, more chances to stand in the dark and watch something brush past. Oumuamua won't return, but will be here, watching. when the next one arrives.